and then promptly return the tests so you can have your test back. All right, John. Is John here? Julian's here. Chad is here. Kaylee. Dalton. Sean. EA? Oh, I don't know. I'm having real trouble with, I'm having a mental block on which Sean is which. Catherine, I do not see. Bradley is here. Eva. Okay, so Michael. Michael sit right there. The other Sean. Marion. Jonathan. Can't be here. Eduardo is not here. Eric. Diana. Shelby not here. Kanan only came for the test. All right. Oh, who am I missing? John? Okay. All right. So we had lots of good scores, but if you're not one of, are you Eva? All right. So, had to be right. If you're not one of those high scores, then on Wednesday, so that panic will not set in. Although a little bit of panic is a good thing because that's a motivator. So we want to take advantage of that little bit of panic and we'll have a brief makeup as I don't know, I emailed you guys, so if you read the email. A brief makeup on Wednesday after the lecture. So we'll stop the lecture at about 9:15, and then we'll have a brief makeup, just brief, right? So because we got to fit it into those 30 minutes. Focusing on just those last 4 problems, 4 through 7. Okay, so problems like those, not those problems obviously, but problems like those you would want to review for that makeup, okay, if you're one of the people who need to raise your score. Now, if you are in the fortunate situation of having a high score, then the makeup is probably not going to benefit you. So there's really no reason to sit for that because you can't earn above 100 in any case. All right, even with the makeup points added, there's no way to get above 100 the way I add points. So it won't benefit you, okay? All right. The purpose of the makeup is to, again, give people who need to review those problems and learn how to do those problems another opportunity to do that, and then also an opportunity to demonstrate that, right, and raise their score some, okay? So between now and Wednesday, right, you'll the answer key is posted, but between now and Wednesday, right, you really want to focus on, seeing if you can figure out, if you did something a little bit wrong, how to fix it. If you were just completely off, right, how to do those problems. Okay. The only major, other than there were individual issues, but things that were recurring in that test were. The one thing I really recall is people not, when it says show something, people were giving me examples and not arguments. Okay, so you have, so I may have noted that on your exam, that what you gave me was an example of, a case where, what I told you to show was true, but you weren't making a general argument for why that was true. Some people wrote too much. So they slowed themselves down, okay? So there's that issue. But we're not going to really have any, on the makeup at least, any, those will be counting type problems, right? So you won't have a chance to fix those issues anyway on the makeup that I'm mentioning. And let's see, was there anything else? Sometimes now when I said give me an algorithm, you would start the algorithm, so you would like tell me the first step of the algorithm, but then you wouldn't really fully describe the algorithm, okay? So for instance of that would be that pyramid problem, okay, right? So where it said, that's problem number 4. So it says, we're built, of course, this is not true, by the way, so, well, not to my knowledge, all right? So we're not planning to build a giant pyramid on the south deck. But anyway, if we did, and we painted the sides red or blue, right, okay, the first part of that problem was, how many ways can we paint how many different ways can we paint the sides of the pyramid? I did not mean to include the bottom, okay? That's apparent, that's going to be sitting on the ground, right? But in the algorithm, so people would say something like, we'll choose a color, either red or blue, for the first side, okay, of the pyramid. Or we'll choose a color red or blue for a side of the pyramid. Maybe not even first side, but just for a side of the pyramid. And then that would be it. That would stop, okay? You see, that's not a complete algorithm for painting the entire pyramid. You're just told me I will, pick a color for a side, right? Okay? All right, so you've got one side painted, right? Okay? But you got to get the other sides painted as well. So you needed a little bit. So I think you probably knew what you probably were thinking the right thing. Because you would often then give me the correct answer to the number of paintings, which is 16, right? But still, you need to be a little bit more complete in your description of the algorithm. So it would be something like, in sequence, right, choose a color for each side of the pyramid, right? To imply that you were going to choose a color 4 separate times, right? Okay? And, of course, that's then how you come up with the cardinality of the, the set of colorings as being 16, or the set of paintings as being 16, right? Okay, that was the other thing that I noticed. Sometimes, your models were, not really fully developed. Well, there's maybe only 1 or 2 problems where you had to write down a model, and then, but y'all were also sloppy about indicating how an element of the model corresponded to an element of the set, right, that you were trying to model. So, for instance, in 5, I mean, right, where you are choosing accounts for that specialist, for that IT specialist, often you would show me an element of the model. So you would say, oh, it's going to be a 3-tuple, okay, and then, but you wouldn't say. But you wouldn't describe the set properly. You would just say, oh, the element of the model is a 3-tuple. Okay, that's fine, but what sort of sets give you tuples as elements, right? So you didn't write down the cross product properly as the set, okay? Or sometimes you would write down the cross product, but then not come back and say, okay, here's a tuple out of the set as an example. Here's a tuple out of the set, and here's how that corresponds to a choice of accounts for the specialist. All right, so look at the answer key, right? It doesn't require a lot of explanation, so it doesn't take a lot of words to do what's asked there in those modeling or algorithm problems. Okay, you can say it pretty quickly. All right, so those were some of the things that I just occurred to me there. All right, so now I didn't put complete explanations on the solution sheet for why the count that I arrived at is the correct count, okay? So you may need to, if you're confused about why the number I wrote there is the correct number, you may need to, on the answer key, right, you may need to come back and, you may need to come by my office, right, or talk to someone else between now and Wednesday after the lecture, so, you'll understand what happened there, right? Okay. All right. So, any other general questions? If you have specific questions about how you were graded, then I'll answer that during office hours. But any just general questions about the test? That's an old homework there, Bradley. Okay, so again, so plan for that if you need to, right? Plan for that makeup on Wednesday. All right. I've already made it up. It's ready to go. So okay. Now also your homework number 3, right? Let's turn that one in on Wednesday. So that'll be out of the way before spring break, okay? And but do y'all have any questions about those problems? So a lot of people have come to my office and asked me about specific questions. So be ready for that one on Wednesday. I think you're in. I mean, I think you're well prepared to do the homework 3, but you'll be ready for homework 4 after, hopefully, if we get through all of our notes today. We certainly will by Wednesday, so that would be due after spring break. Okay, we just have a few more things a few more of these elementary counting techniques, and then we'll take a break for a while and talk about something else from another topic from Combinatorics. Then we'll come back to more advanced counting techniques because we still have not talked about the more general version of inclusion-exclusion. That's going to give you a workout. Yeah.
When exactly is spring break?
Next week.
Oh.
Yeah. Okay. So spring break is next week, right? Kaylee's the only one that missed that. Okay. Yeah. Spring break is next week. So it looks like the weather is going to cooperate. I think we're past the cold weather, so maybe some, not warm weather, but hopefully no more weeks like last Wednesday. That was cold. Okay, so no questions. We're ready to finish talking about these elementary counting techniques. Then we're going to take just a little bit to apply this to the topic of finite probability. Probably many of you already know how to compute finite probabilities, simple finite probabilities, because it's all derived from counting. So many of the lots of you are familiar with have practiced counting techniques before a little bit. You probably did that in the context of finite probability. We're going to revisit that just a little bit today, but not a lot. Okay, but this is not a probability question. We were in the middle of an example before the test last Monday at the end of class, and we hadn't finished it. So I want to finish this example and then go on to some maybe similar type examples. So we were looking at the topic of, we were thinking about the topic of combinations. That's a particular set model that we use for counting a lot, okay? And a combination is just a subset of a given set, all right? And frequently we're interested in counting all of the subsets of a particular size from a given set, okay? And so, again, those are referred to as, in this context, as rather than subsets, as combinations, okay? Remember, when you build a subset of a given set by implicitly, right, you also are building the complement of that set, right, okay? Because you're thinking of your larger set as the universal set. So if you pick a subset of the larger set, then you're sort of implicitly, right, not picking another set, right, its complement. So whenever you're counting combinations, you're also counting complements of these combinations as well, right? So sort of keep that in mind. All right, so this is a very straightforward combination problem. Not completely straightforward, but pretty straightforward. So we were talking about selecting teams of 5 from the class. So our class has shrunk a little bit, but we're going to stick with 20 that were on the original roll, okay? And so we were picking teams of 5, right? And so the very first question that we ask is, how many teams of 5 can you choose, right, from the class, right? And so if you let that S be that set of teams, of size 5 there, right, then what we were practicing, again, in this example, is working with or modeling this set, right, with a set of combinations. So this is my notation for a set of combinations. This would be, in particular, choosing subsets of size 5 from a set of size 20. Of course, our standard set of size 20 would be an integer segment 20, right? Okay, so when I use this notation, I'm frequently referring to, again, all, right? Okay, this is a set of sets, so all sets of size 5 from the integer segment of size 20, right? Okay, and of course that's clearly going to be a model for the set of teams, right, of size 5 from the class, right? Okay, if we just think of numbering the students in the class, right, from 1 to 20. So that set of teams, right, is I shouldn't use equal here. No, okay. It's okay to use equal here. So this set is a model for this combination set, right? Is a model for that set of teams, and so they have the same cardinality, right? So, right, there's a 1-to-1 correspondence right here between S and M, okay, and so they have the same cardinality. And we learned before the test, right, how to count that. The cardinality of that set of combinations, right? Here's the notation we use for that cardinality, right? You put in the parentheses 20 over 5. Notice this is not a fraction, right? Okay. The way you read this off of the page is 20 choose 5, all right? And here's how, and this is the value of 20 choose 5, right? So here's how you evaluate this notation. It's just going to be 20 factorial, the number on top, divided by 5 factorial, and then 15 factorial as well, okay? The reason these two factors are in the denominator, right, is because, remember, when you choose the set of size 5, right, you are implicitly also choosing its complement, which, since the set has size 5, right, the complement is going to have size 15, all right? So remember, subsets do not have an order, right, okay? So this is different from the permutations of size 5 from a set of size 20, right? There are going to be a lot more permutations of size 5 than there are subsets of size 5, right? Because subsets of size 5 do not have any particular order. All right. Now, well, so we can do these calculations, of course, and compute this number as long as we can interpret the factorials right, which is not so hard to do, right? Okay. But I'm not usually so keen on computing these actual values. Remember, 20 factorial, right, means 20 times 19 times 18, right, all the way down to 1. Of course, 5 factorial is 5 times 4 times 3, right, all the way down to 1. And then 15 factorial is 15 times 14, right, times etc., all the way down to 1, correct? Okay. So you can, of course, reduce this fraction quite a bit, right, because you have lots of common factors in the numerator and denominator. So immediately the 15 factorial and the 20 factorial will reduce each other, right? So when you divide 15 factorial from 20 factorial, you're going to get left with just 20 times 19 times 18 times 17 times 16, correct, right? Because the 15, 14, etc., those factors will cancel with the 15 factorial over 5 times 4 times 3 times 2 times 1. And then you can do a lot more reducing, right? 5 times 4 is 20, so you can immediately reduce that, correct? And let's see, what else can we reduce here? 3 times 2 is 6, right? And that's going to go into 18 3 times. So you just ultimately end up here with 19 times 3 times 17 times 16, whatever that product is, okay? These combination values, right, okay, they always reduce to they're always going to reduce to integers, right? Because remember, this has to be a whole number, right? We're computing how many subsets of size 5 we can choose from a set of size 20, right? Well, obviously, that's got to be a whole number. So if this computation is correct, it has to reduce to an integer, okay? Which, of course, it does in this case, whatever that quantity is. All right. Oh, by the way, remember now, this is called... that calculation there, that's called a binomial coefficient. And there's a particular reason why that's called a binomial coefficient, which we'll hopefully we'll get a chance to explore in depth later, right? Okay. Binomial is an algebraic term, so notice that we're making a link here between algebra and and combinatorics, right, and counting. That link is going to be useful to us in the future, okay? That connection will be useful to us in more advanced counting problems in the future. Because we know lots about algebra, so if we can apply our knowledge of algebra to counting, that's probably going to benefit us in terms of counting. May benefit us in terms of algebra too, I don't know, okay? So, all right. Let's make it, so there's no questions about that, right? Okay. Oh, we're not through with the problem, right? Okay. So there we just counted the set of teams of size 5, right? Okay. I had already done that earlier, but this question is a little bit more complicated, right? It says Taylor and Eric refuse to be on the same team. So we cannot pick a team with Eric and Taylor on them. All right. All right, so how can we count this this set of combinations, right, where Eric and Taylor are not on the same team? Yes, Eric. Use a complement, right? This sounds like a complement problem, right? That's excellent, all right? So that sort of recognition is going to be useful to you in counting, right? Okay, this looks like some sort of complement, right? So what would you suggest there, Eric, to... Yeah, but back up there. So what's your grand strategy there? You're sort of telling me how to do the counting, but even before we get to that point, what's your strategy here in using the complement? You see what I'm asking here? Okay. Yeah. What's the set and what's its complement that you're counting here? What? So what? The big set is what? No, you're backing up a little too far, right? Okay, all right. So can y'all help explain what Eric is trying to tell me?
Yes.
Yeah, Sean.
So our big set that we want is what we just calculated.
Right. So that's the set of teams of size 5, right? Okay. Yeah.
And then we want to subtract the teams with Taylor and Eric.
Right. Okay. So yeah. So we're going to define teams with Taylor and Eric, right? Okay, because what we're really looking for are teams without both of them, right? Okay, so let's count the teams where they both are there, right? Okay, so what shall we call that set? T. All right, that's what I was thinking. Also, so teams with, right, Taylor and Eric. And so, Eric, you already told me now how to count this, right? So how big is this set T? I'm running out of room here. So how big is this set T, Eric? So you don't worry about describing the model for me, okay? So we don't have to go through that much formality. Just can you count this for me? What now? 20 choose 3, right? Okay. So tell me, where did the 20 choose 3 come from? So why did you pick that binomial coefficient? I think everybody knows, but I'm just getting you to say it for me. All right. Right. So see, what you're implicitly describing here is an algorithm for building a set for building a team in T, right? Okay. So what's your algorithm for building a team that's going to be part of T? Taylor and Eric are both on the team, right? So what's your algorithm for creating such a team? Oh, they're both going to be in it, right? Okay, so you're going to just put them in there, correct, right? Yeah, so there's the first step in the algorithm. We're just going to put automatically Eric, you, and Taylor on the team, right? Okay, all right, so those are done. Then what's the next step? Well, I don't think you said choose the next person. I think you went ahead and said we're going to choose the... I don't think we're choosing one person at a time, right? The other 3, right? Yeah, you said then we're going to select the other 3, right? Yeah, you have to be careful there about going one person at a time in choosing the 3, okay? Because that implies that the order in which you choose the remaining 3 is important. So you're going to end up overcounting that way, all right? So better just to say I'm going to grab 3 all at once, right? Okay, yeah. And how many ways can we grab the 3?
So would it be 18 choose 3? Because I mean, technically
Oh, I see. Right. Okay. So it's 18 choose 3, right? Okay. Because what? Oh, yeah. Taylor and Eric are out of the pool, right? Okay. Oh, all right. So great. See, when we slowed ourselves down and thought about that a little more carefully, right? Okay. We corrected our mistake. Okay. So this is why I'm always trying to encourage you to think of what is the algorithm, right, that we're using to create an element of our set, or what is the model that we're using for the set, okay? Because when you slow down and think carefully like that, it can help you think better about the problem, right, okay? All right, so that's 18, choose 3, right? And then, so what's our final answer here? What we're really interested in is what? Not T, right, but... Yeah, what's the set that we're actually counting here? Teams without both Taylor and Eric. That's T what? Complement, right. That's T complement, right? Okay. But you know that T complement there is going to be, right? Okay. This, right? That's the universal set, right? The set of all teams of size minus this, right? 18, choose 3, okay? So... and then we can just do those computations, right? Okay. Excellent. Right. So there's the answer. Oh, great. I'm glad you said complement, right? So I'm glad you're thinking now in those terms. That shows progress there. All right. So now let's think. There's another idea other than complements, right? So that we also want to make sure that we're applying properly. So let's see. At the end of the competition, 3 Snickers are going to be awarded as prizes. Okay. So how many ways can the Snickers be distributed to the team? Okay. How many ways can the Snickers be distributed to the team? Now, Snickers typically all look alike, right? Okay, so I don't know if they have serial numbers on them or not, but Snickers tend to look very similar to one another, right? So we really cannot distinguish one Snicker from the other, all right? So you want to keep that in mind. By the way, well, let's try answering this one first, and then we'll go back to the simpler problem, which is what if we had 3 different candy bars, okay, and we want to distribute those amongst the team, right? Okay, that's a little bit easier counting problem. All right. Typically, when in these counting problems, so you want to watch for this in these counting problems where you have indistinguishable objects. Somehow involved in the problem. Maybe not all the problems are maybe not all of the objects are indistinguishable, but when some of the objects involved in the problem are indistinguishable, that makes the counting problem harder. Okay, so be aware of that. And this is what's happened in this case, right? Okay, because Snickers all look alike. However, the people are not all looking alike, right? Okay, so we can distinguish the 5 team members. They are different, but the Snickers are all the same. Who came in that does not have a test? Who are you? Michael? Okay, so I do have a test for you. And an old homework, too. It's your lucky day. Okay. All right. So let's see if we can figure this out. Any ideas? I think you want to. Think about breaking this up into cases. All right. This is the other key idea I wanted you to. This is the other key idea I wanted you to recall. Right. So complements is important also. Okay. But when I say breaking this up into cases, let's see if we can. What I mean here is breaking this big set that we're interested in counting, right? Okay, breaking that into smaller subsets, hopefully that do not overlap. Okay, all right, so that we can add the size of those smaller subsets together to get the size of the big set, okay? So, well, let's describe the set here that we want to count. So we want, or give it a name. I'm almost going to be rewriting the words in the problem, right? But what name do I want to call this? I would, okay, all right. S, unfortunately, we've already used. I would say S for Snickers here, right? But, oh, you're thinking W for what? Ways to distribute the Snickers, right?
I'm thinking winners.
Oh, winners? Okay, all right. So ways to distribute the Snickers here. All right, so that's our big complicated set, right, that we're going to count. So what I'm thinking here is, can I possibly break this up into some subsets, okay? Hopefully, Sean, that don't overlap, all right? Because if they overlap, then I'm going to be in trouble. If they don't overlap, right, I can just take their union, right, and get the bigger set. Well, I may be able to do that anyway, whether they overlap or not. But when I'm counting the union, right, I can just add the cardinalities of the small subsets, right? That's just the simple version of inclusion-exclusion, right? Okay? So, all right, so I'm talking over you there. You're probably way ahead of me. What were you going to suggest?
I was going to say, for one set, we can choose ways people can get free candy bars.
Okay, that's a good place to start, because that's easy to count, right? Okay, so so this is what are you saying there? Ways one person gets 3 candy bars, right? And that, I think, is trivial almost, right? Okay, because so we can just write this down immediately. It's 5, right? Okay, you just have to select the person, right? Okay, and then you give them all the candy bars, correct? Right? So obviously that is 5. You can also, by the way, think of this as 5 choose 1. Okay, just to keep in the spirit of combinations and binomial coefficients, since that's what we're dealing with here, right? Because you've got to pick that one person, right? Okay, and then give them all the candy bars, correct? Okay, so yeah, so I don't think anybody's going to fight with us over 5, right? Shelby, did I give you your test back? I did. Okay, all right. So all right. So what next now? So, but obviously, it may not be the case that every person gets 1 candy bar, right? So what other cases do we have here, right? What other subsets? Okay, well, so...
Like
One person gets 2 and another person gets 1.
there you go, right, okay. So... So way one person gets 2 and another gets 1, right? Let's come back to this to count it. What's the obvious third situation here? What? Yeah, that's right. So. All right, so W3 there is pretty easy to count, right? Okay, so how is it that 3 people can get 1 candy bar? So if you're going to make this distribution, what algorithm would you choose, right? What choices would you make? Eduardo, what choices would you make if you want 3 people to get each to get 1 candy bar, right? So. Yeah, so yeah, everybody's only going to get 1 candy bar, so that means that 3 people are going to get 1 candy bar. 2 people are left in the dark, right? But 3 people get 1 candy bar, right? Okay, so how can you do that, right? What would be an algorithm for making that sort of distribution? Just what choices would you make? So if I asked you to, if I gave you 3 candy bars and said, here's the class, you got to give 1 candy bar to 3 different people, right? Okay, what would you do?
Assuming that the class size is still 20,
Mm-hmm.
choose 3.
20 choose 3, right, okay, because what are you choosing there? Just, what's the 3?
The candy bars. Or the people.
The people, right, okay, yeah. So you choose 3 people out of the class, right, and you give them 1 candy bar each. Sure, right, okay. So now, by the way, it's important there. Wait, let's go back to that algorithm just a second, although it's very simple, right, okay. You're going to pick the 3 people to whom you're going to give the candy bars, right, okay, and you give them. But here's where it's really crucial that the candy bars are all indistinguishable, correct, right, okay. Because if I chose 3 people and I had 3 different types of candy bars, I could distribute them in different ways, right? Okay. Yeah, I could rearrange, right, who got which candy bar, and that would be a different distribution. But since they're all Snickers and they all look alike, right, moving a candy bar from one person to the other makes no difference, right? So you're right, it's just 20 choose 3, okay? Great, so that's done. Now we just have to go back and count W2, right? So here we're 20 choose 3. All right, so let's see now if we can count W2. Sean, what were you going to suggest there?
Wait, that means 5 choose 3.
5 choose 3. Well, because I'm focusing on the class, right? Because that's what Eduardo said. Yeah, it's the team that we're working from. I told you wrong because I said you're going to pick 3 people out of the class, right? But it's from the team, right? Okay. So that's 5 choose. Is that right?
No, I mean 5 choose 3.
Oh, okay. All right. Now, what about W2 then? Okay. So how can we give 2 to one and 1 to another? So, what, John?
4 to the 5th, because you can only give one person 2, but then there's 4 ways to do that. So for one person, there's 2, 1, 2, 0, 1. I'm placing these. I'm trying to explain this very well, but there's 5 ways to do that.
Oh, well, yeah, but I think let's get into the spirit of combinations, right? Okay. So, Bradley, what were you going to suggest there?
5 choose 1 and then 5 choose 1 again. Just because you choose one person to give 2 and then another person to give 1.
Oh, I see. So you're saying, but wouldn't that be 4 choose 1? Yeah, okay. Oh, I see. So here, someone getting 2 and someone getting 1 that's a different situation, right? Okay. So the person that gets 2, we can distinguish from the person that gets 1, even though the candy bars are all alike, right? Okay. So I think Bradley's solution is correct. Let's pick the person who's going to get the 2, right? Okay. And then we have to pick the person who's going to get the 1. But once that's done, once the first person is chosen, there's only four ways to pick the second person. Yeah.
So are you adding those or are you multiplying them?
I think we're multiplying them, right? Because aren't we making a choice in sequence there, right? Okay. We're making a choice in sequence, right? You pick the person who's going to get the 2, right? That's 5 choose 1 ways to do that. And then we pick the person who's going to get the 1. There would be 4 ways left to do that, right? Okay. So you can write this down in terms of combinations, right? But you could also just think of it as I've got 5 people I can pick from to give the 2 to, and then I've got 4 people to pick from to give the remaining Snickers to, right? So this is going to be 20. I had a slightly different way of thinking about this. So let's see if this also comes out to be 20. If it doesn't, then we're going to have to rethink something. Here's another way of thinking about this. Pick the 2 people who are going to get the candy bars, right? Okay? Pick the 2 people who are going to get the candy bars. So how many ways can you pick the 2 people to get the candy bars? That's 5 choose 2, right? Okay? So there you pick the 2 people, but then you have another decision to make, right? What's the second decision? Who gets the 2 and who gets the 1? So how many ways can you make that decision? 2, right? Okay, right? Okay. So you have to take this binomial coefficient, right? This combination, and multiply it by 2. Okay, because once you pick the pair, you have to decide where to give the 2 and where to give the 1, right? There's 2 ways to do that. Let's see, what does this turn out to be 20? Let's calculate that. So that's 5 factorial over 2 factorial, 3 factorial, right? Oh, but then we're multiplying by 2, correct? So these will divide out, because 2 factorial is 2, and then 5 factorial over 3 factorial is indeed 5 times 4, right? So we get 20. So, all right, that gives a little bit of confidence that maybe we're counting correct, right? Because thinking 2 different ways, we got the same answer. Yeah, Kaylee.
Alright, so then when we're calculating the cardinality of W, that's when we add the cardinality.
That's when we add, right, okay? Because these 3 sets are a partition of W, correct, right, okay? All of our ways to distribute the Snickers has to be in one of these 3 sets, correct, right? That's the only way to distribute the Snickers, right? 3 people get 1, or 2 people get the Snickers, right? 2 for 1 and 1 for the other, or 1 person gets all 3 Snickers, right? That's it. That's the only way you can distribute the Snickers. So every element of W is in either W1, W2, or W3, but these sets are all disjoint, right? They do not overlap, okay? So so we just add there to get our final answer. Where can I squeeze that in? So W is going to be the sum of these 3, correct? Which I didn't calculate. This one is 5, right? And then the second one is 20. Did we ever compute the 10? Oh, you did? Okay, all right. So it turns out to be 35. Nice. All right. All right, now I'm going to make it just way harder. All right, okay. So we got away with breaking it up into this partition of 3 subsets in this example because we only had 3 Snickers. But things get way harder when you up the number of Snickers. All right, so suppose we have 10 Snickers to distribute amongst the team members. Okay, all right. So now how can we do that? All right, yeah.
Specifically, would you say that it gets significantly harder when it's an amount equal to or greater than the amount of people to choose from? Because we had 3 to separate.
I'm not sure it's that. I think it's just it's the number of Snickers that we were distributing. That was 3 is pretty small, right? Okay, so so that simplified matters. But now with 10 Snickers, it's going to be well, just think of trying to break that up into cases, right? You're like we did this one. You could attempt that, but that would be a lot of cases to think about, right? Okay. So so let me show you another way. All right. So here's now where we're going to this may be the first time where we're going to have sort of a double indirection. Okay, so I want to model my set that I'm trying to count here, right? I want to model that, right? I want to build a model for that, and the model is going to look quite a bit different initially from the set. All right, so let me show you how we're going to think of this. Okay, so all right. So we need a name for the set that we're trying to count here, right? So what do you want to call it there? I was going to go with W again. Okay. All right, so okay. All right, so here's what I'm going to do, all right? I'm going to, so we've got 5 people, right, okay? We've got 5 people now that we're going to, that we have to award the Snickers to, correct? So I'm going to write a sequence here of, symbols on the, I'm going to write a sequence of symbols down, okay? And And I claim now that the ways that you can arrange the symbols will correspond to the distribution of the candy bars. Okay, so we're going to build a model for our set W, but that's not going to be ultimately the set that we're going to count. All right, does that make sense? So I'm going to build a model for W, and then I'm going to have to build a model for the model for W. This is what I mean by sort of double indirection here, okay? So I'm going to think of W, let me put it this way, I'm going to think of W in a different way, okay, in a set that we can build a model for to count, all right? But these sets are all models for each other, so if we can count the last one, then we'll be able to count W as well, okay? All right, so, but before I describe what that intermediate set is, I'm going to draw some, again, I'm going to draw a sequence of symbols here on the screen here. Oops, let's see, did I do that right? No. Okay, I think I did that right. All right. So that's clearly just a sequence of what? Well, those are supposed to be zeros, but you can call them anything you want, circles if you like, all right? So, and of course, what else there?
There's 10 of them?
There's 10 of the circles, right? So that's kind of a key, right? Okay, and then plus what else there?
4 slashes.
Yeah, 4 slashes, right? Okay. Now, so that's just a sequence of circles and slashes. But I claim now that there is a correspondence between that sequence of circles and slashes that matches a distribution of the candy bars. So, can you see what that's going to be?
Is it like 3 goes to the first, 4 goes to the second person, 1 goes to the third, 2 goes to the fourth, and the last person gets nothing?
That's it, right? Okay. So this corresponds to person 1 gets a 3, right? Now remember, the people are the people we know, right? Okay. So the people are distinguishable. That's important, right? Okay. So we can distinguish the people from one another, all right? But we can't distinguish the candy bars, right? Okay. So yeah. So indeed, this circle, this sequence of circles and slashes there, that's going to correspond to this distribution of the candy bars. All right. So person 1 gets 3, person 2 gets 4. Person 3 gets 1, person 4 gets 2, and person 5 is out of luck. They don't get anything. So, Sean, if I write a new sequence of circles and slashes, right? Okay. If I write a new sequence of circles and slashes, then can we easily discover what the distribution is going to be? So, give me another sequence of another rearrangement of these symbols, but it's got to be these symbols, okay? So that's 10 circles and 4 slashes, okay? So just give me some other rearrangement, right?
0 slash 0 0 0 0 slash.
So how many zeros did you say there? Was that right?
Sure.
Yeah, okay, all right.
0 slash 0 slash, and then 2 more. Here.
Well, count there. 0 0?
Yeah.
There we go. Okay, is that it? I think so. All right. So, yeah, there's another sequence of those symbols, right? And but now what distribution does that correspond to of the candy bars?
Person 1 gets 1 candy bar.
Right, yeah, yeah, exactly right. So it's pretty easy, right, to see how that sequence of circles and slashes, right, corresponds to the distribution of the candy bars, correct? Okay. That's how many go to 1, right? This is how many go to 2, correct? This is how many go to 3. This is 4, right? And this is 5. Okay. So if I write down any rearrangement of the circles and the slashes correct, you're going to be able to tell me what the distribution of the candy bars are, or vice versa. If I gave you a distribution of the candy bars, right? If I told you here's how the candy bars were distributed, could you write down for me the corresponding sequence of the circles and slashes? Sure, right. Okay, I think you could, correct? Including this one. Did I get enough there? And including this, right? Which means what? Yeah, person 5 gets all of the candy bars, correct? Right. Okay. So this is going to be my initial model for W. Okay, that's my initial model for W. All right. So y'all want to call that? I don't want to call that M. So because there's another model coming in here. What? I? All right. Okay. I wasn't expecting that, but that's fine. All right. So Kaylee, how would you describe I in words? Ways to do something. No, it's ways to arrange. What are we arranging here? Yeah, how many of them though?
10 zeros and 4 slashes.
Yeah, 10 zeros and 4 of the slashes, right? Okay. And I think we've convinced ourselves that these two sets, at least I hope I did, that these two sets are in fact models for one another, right? Okay. Well, more specifically, I is the model for W, all right? There's a one-to-one correspondence between these arrangements and the ways to distribute the candy bars, all right? Okay, now, all right, so I've translated one problem to another, right? I've translated this counting problem to this counting problem, but I'm hoping this counting problem now is easier, okay? Now, so I want to see if I can write down a model for I, all right? That is going to be M. Okay. Hopefully that's a set that I'll be able to count. Okay. So that's what I'm hoping for. All right. Any suggestions there on what M should be? So how can we count the number of arrangements of? How can we count there? The number of arrangements of these 4 slashes and 10 zeros. Well, let me point out that when you write down, so this is a little bit more familiar problem to you, right, than the first one, because this is a problem that involves strings of characters. And we've solved lots of problems involving strings of characters, correct, right? Okay. So we at least maybe have a better chance of solving this one. So when you write down this string of characters, how many characters are involved there? 14. That's right. You've always got 14 characters, correct? Right? Okay. So and they're they're arranged from left to right, right? So you have here really 14 when you're creating one of these strings, right? You really have 14 what? 14. Well, 14 objects, right? What would you call those objects though that I'm referring to? Yeah. Well, okay. So. Positions, right? We really have 14 positions, correct, right, that we have to fill up when we're creating one of these strings of slashes and zeros, correct, right? Okay, we have to fill up 14 positions. And those 14 positions, though, have to be filled up with what? What's your only choices in your... Yeah, slashes and zeros, right, okay? So notice what you're really doing there is you're really choosing, right, which positions are going to get what? Slashes, and which positions are going to get zeros, right? Okay? So you've got this set of positions. How many positions do we have? Right? And you're breaking them up into 4 and 10, right? 4 and 10 what? element subsets, correct? Right? Yeah. You have the subset of positions that get what? Slashes. And you have the subset of positions that get what? Zeros. Well, actually, that's all the other positions, right? Because you've only got slashes and zeros, right? Okay. So, really, if you choose the set of positions that get the slashes, you automatically what? You automatically get the rest, right? You automatically know where the zeros are going to go, correct, right? Because fortunately, we only have slashes and zeros here to work with, correct, right? So, what am I really doing when I'm building a string of the slashes and zeros? What's my algorithm? So easy. No, what's the algorithm? Say the algorithm first. What am I really doing?
Pick where the slashes go.
Pick where the slashes go. That's right. You're going to pick where the slashes go, correct? Right, okay? How many ways can you pick where the slashes go? That's equivalent to doing what? Yeah, so when you say 14 choose 4, that's equivalent to picking what? Yeah, so you're picking the what to put the 4 slashes. The positions, right, okay? You're just picking the positions to put the 4 slashes, correct, right, okay? So in effect, you're choosing how big of a subset from the positions. 4, a 4-element subset from the positions. What's the set of all 4-element subsets from the set of positions called? That's called the 4 combinations, right? Okay, that's the 4 combinations from the set of positions. All right, so what is my set model here? What is M? What's the set first? Not. Don't tell me it's cardinality, but what's the set?
The ways to arrange.
Not arrange. It's a combination, right? Okay. What are we doing? We're picking what from what? 4 from 14, right? Okay. We're picking 4 things from 14. Now, this means you're picking 4 numbers from the integer segment 14, but that's really the same, right? Okay, because you've numbered the positions 1 to 14 from left to right, right? Okay, so you're picking 4 positions from the 14, right? All right, that set now corresponds to this one, okay? So that is a model for the set I. Well, since I is a model for the set W, then we also have what? That's right, okay? We have that M also, yeah, I wrote it down wrong. So we have that M also corresponds to W, right? Yay! How big is M, though? So, yeah, it's this binomial coefficient, right? 14 choose 4, right? Which is, what'd you say there? 13 times 11. What happened to the 14? Did that cancel?
It cancels down to 7.
Oh, I see. You're giving me the final calculation here. What does it turn out to be? 13 times 11 times 7 after you've done the calculations and reduced. Okay. Ooh, nice. All right. So that's not a bad number. How big is that? 1001? Exactly 1001? That's it? Oh, cool. All right. There we got it. All right. Now, did you follow all of that? Think you can do that again? Yeah, Chad.
Well, my question is, why wouldn't it just be like 5 to the 10? Wouldn't that total answer be? Because wouldn't you just be able to like choose, for each Snickers bar, you have 5 people to choose from, so it would just be 5 times 5 times 5 all the way to 10?
Yeah, that would be if you could distinguish the Snickers bars. Okay, so if you knew that if you had a way of distinguishing one Snickers bar from another. Okay, because think of it like this. All right. We were going to ask your question in an earlier example, but I forgot to go back and ask that to clear that up. Back in this easier example where we were distributing 3 Snickers bars, okay, amongst the 5 team members, all right? So we had this, a method for counting that, right? Okay. What I forgot to ask was, what if it were 3 different candy bars, right? So what if it were 3 different candy bars? Then your answer, the way you described, would be correct, right? Okay. Write down for me. Can you suggest 3 different candy bars for me? So one of them might be Snickers, right? What's another candy bar? Huh? Twix. And Hershey's. Okay. So indeed, suppose that we had, go back to this example where we had 3 candy bars amongst the 5 people, right? Okay. So you have to choose how to distribute the Snickers, right? Okay. How to distribute the Twix and how to distribute the Hershey's, correct? Right. So you say, well, how many choices do we have here? 5, right, okay. So there's 5 ways there to choose the person for the Snickers, right? How many for the Twix? 5, right, okay. And since people can get multiple candy bars, right? And for the Hershey's, there's 5, right? So indeed, in this case, the answer is 5 to the 3rd power, all right? But now let's look there at a specific choice of the people. So, maybe person 1, right, gets the Snickers, correct? Person 1 gets the Snickers. Person 2 gets the Twix, and person 2 gets the Hershey bar as well, correct? Right? Okay. So that's a distribution of the candy bars. Okay, and this would be a different distribution, right? Because this person still got 2 candy bars. This person only got 1 candy bar, but this person got a different combination of the candy bars, right? So when you count this as 5 to the 3rd power, these are different distributions. When the candy bars are different, these are different distributions. But what if these were all Snickers? This would be the same distribution, right? Person 2 would get 2 Snickers. Person 1 would get 1 Snickers, right? Okay. So you have overcounted. In this problem, this way of counting would not work, right? Okay. That's the same problem. So the same issue is going to occur when you're passing out the 10 candy bars. Everyone see that, right? So if the candy bars are different, you get a much larger number of distributions. Okay. That's why I was warning you at the beginning. When you have indistinguishable objects involved in a problem, that tends to complicate the counting. All right. So you have to think about it differently. Wow. Let's see. So I'm just going to repeat what I said, okay? So a subtle but key assumption, all right, in that previous problem is the individual students were identifiable. The candy bars were not, right? Suppose you take that assumption off, then that makes the logic even harder, all right? Let's look at this problem. Suppose you have the candy bars are different, okay? So you have different candy bars, but you're going to distribute them to identical twins. All right, Chad, so you can help me with this problem now because this is similar to what you were thinking, right? Okay, but it's not the same because now the people cannot be, the candy bars are different, but the people cannot be distinguished. All right, so we're going to assume that the identical twins cannot be, we cannot tell them apart. All right, so in how many ways can we distribute the candy bars? All right. I think this one is fairly easy because this type of problem can be really hard, but this one is fairly straightforward. Go ahead and think of it in your way where the twins are distinguishable. All right, so pretend that we can distinguish between the twins. Then, how many ways could we distribute the 5 candy bars? That's 2 to the 5th power, right? Okay, yeah. Okay, so if the twins are distinguishable, the number of ways of distributing the candy bar is 2 to the 5th power, because you're thinking, here are my 5 candy bars, right? Okay, 1, 2, 3, 4, 5. Let's number them, so we don't have to make up any more names, okay? So there's my 5 different candy bars. If I want to make a distribution, right, I simply, make a choice in each case of which twin, right, okay, to distribute to. Let's number the twins, 1 and 2 as well, right, okay? So how many choices do you have for the first one? It's 2, right? For the second one, 2, etc. Okay, so the total number of ways of distributing the candy bars in that case is 2 to the 5th. But now, Chad, what if the twins are, unfortunately, not distinguishable? Okay. Not quite, okay? That's the next problem, all right? But you're on the right track, okay? So the twins are not distinguishable, but the candy bars are, okay? Yeah, let's, by the way, what set model, when we're counting this, we describe this as an algorithm, right? Okay, I have to distribute the first candy bar, right? I have 2 ways of doing that, right? I have to distribute the second candy bar. I have 2 ways of doing that, right? Okay, etc. So multiply all those choices together, you get 2 to the 5th power, right? Okay. If the twins are distinguishable. What's the set model we're using here, though, in this case? What is that cardinality? What does that number also correspond to as a cardinality? Cross product, right, yeah. So what cross product there would it be to give you this cardinality? Wouldn't that be, let's use the integer segment 2, because we've got twin 1 and twin 2, right? And then cross product with itself 5 times, right? Okay. What sort of elements live in here? Well, what sort of creatures are in this is a set, right? What sort of creatures are in this set? What? 5 tuples, right? Okay. So, and of course, the cardinality of this is still 2 to the 5th power, right? Okay. But what's let's take an example of a 5 tuple that's in this set. So, give me a nice 5 tuple out of this set. 1, 2, 2, what? 1, 2, right, okay. So what is that distribution, Kaylee, of the candy bars?
The first and fourth candy bar go to the first twin, and then the second, third, and fifth go to the second twin.
Right, yeah. So twin 1 gets the first candy bar, twin 2 gets the second candy bar, twin 2 gets the third candy bar, right? Twin 1 gets the fourth candy bar, twin 2 gets the 5th candy bar, right? Okay. Remember, the candy bars are distinguishable from one another, right? Okay. And we're assuming here that the twins are. But what if the twins are not indistinguishable? Okay. So right, okay. Which candy bars are paired with which candy bars, right? Okay. My point is, if the twins are not distinguishable, then this tuple and this tuple are the same distribution, aren't they? There should be what? Oh. Oh, this. No, I flipped it, didn't I, right? Yeah. Isn't this the same? If the twins are not distinguishable, this is the same distribution of candy bars, right? Okay? Because you cannot distinguish twin 1 from twin 2, right? In our problem. Okay, so we have overcounted here, but by how much?
5 by 2.
Twice, right? Okay, because each distribution, correct? Okay, in this set, right? If we just reverse the components, right? Okay, that would really be the same distribution if the twins are not distinguishable. Okay, so you have overcounted by 2. So the right answer is this, just divided by 2. So it's 2 to the 5th divided by 2, which happens to be, interestingly, 2 to the 4th power. Wonder how we can come up with 2 to the 4th power directly there without dividing by 2. Wonder if we can think of a set model that counts immediately as 2 to the 4th power. That's good. All right, so you see the issue here, right? Okay, with the twins being indistinguishable. Chad, now I think you can answer this question. What if everything is indistinguishable? Okay, so we cannot distinguish the twins, and we've got 5 candy bars that are all alike. Then, what are the different ways of distributing them? Well, what's one way? 5 to 1 kid, right? Okay, right. So, see, it could be that one kid gets 5, okay? But you can't say twin 1 gets 5 versus twin 2 gets 5, right? All we would know is one of the kids is sitting there with 5, right? Okay, so that's it, right? Okay, that's one of them. Can you now just by observation figure out the other ones? Okay, so it could be one twin gets 5, right? What?
Would it just be 5?
I don't know. So one twin gets 5. What's another possibility, Shelby?
1 gets 4 and 1 gets...
Oh, there we go, right, okay. So one gets 4, right?
3 gets 3.
All right, so one gets 3. And are you going to tell me that, are you going to tell me 1 gets 2 is a different one?
They will be the same as 1.
That's right. So this is not correct, right? Okay. If one of them gets 2, that means the other gets 3, but then you're back in this case, correct? So how many are there? 3, right. Okay. In that case, there's only 3 ways of distributing the candy bars. Okay. Ooh. Hard, right? Okay. I told you the logic gets harder. The counting gets easier, but the logic gets harder. Yeah.
I'm trying to think of a simpler way to say why that is. Like, more for math.
I'm not sure there. Well, yeah. Okay. So there are. Yeah. So this is a mathematical problem, and there are models developed for this. Okay. But right now we're not there. We're just handling it on a case-by-case basis, right? Okay. Sometimes that's how we count, right? Okay. Just have to think about what the different possibilities are. But you do understand why these are the possibilities, right? Okay. If you got 2 people sitting there, you can't tell one from the other, and you can't tell the candy bars from one from the other, right? All you can tell is, okay, one got 5 and the other got nothing, right? Okay. That's all you know, right? Or one got 4 and the other got 1. Or one got 3 and the other got 2. It can't be one got 2 and the other got 3, because that is the same as one getting 3 and the other 2, right? You can't distinguish the 2 people, okay? So there's only 3 ways of doing it then. Much different. All right. Okay. We're out of time. Let me just show you this definition, okay? We've been breaking things into... We've been breaking sets into subsets, right? So, and again, whenever you create a set, you automatically have its complement, all right? Now we're just going to generalize that a little bit. Suppose we break a set into a list of disjoint subsets, okay? In other words, a partition, okay? And we're going to indicate how many elements are in each one of the partitions. But the partitions have to subsume the whole set. They have to consume the whole set, right? Okay. So earlier we were just looking at a partition with a set and its complement, right? Okay. But now, what if we break the set up into multiple subsets? Okay. Not just a set and its complement, but a series of subsets. But again, the union of the subsets is the whole set, and the subsets do not overlap. Okay. Again, that's called a partition, right? And what this theorem tells you is how many ways you can partition a set, okay, into a collection of subsets, right? Okay. But we have to indicate how big each one of the subsets is going to be. Right, so these numbers tell you how big each one of your subsets is going to be. Notice this formula is just the same as the a combination formula, right? Okay, except there we had just two subsets, a set and its complement. Here you can have multiple subsets, but the formula comes out to be identical. Here's our notation for this number. This is called a multinomial coefficient. All right, so. We're going to practice using partitions also. Well, we already have done this, right? But a little bit more complicated partitions as set models, okay? Next time. It'll be very similar to what we just did, okay? It's just a generalization of what we've just done. Okay. All right. Well, so I'll see y'all on Wednesday then, right? So be ready for that to make up, right, if you need to take that, okay? And we're going to turn in homework on Wednesday, homework 3.